So today we're going to look at similar triangles. Similar triangles are basically triangles that are very similar. They basically share the same shape. So for instance, I could take this triangle, I could copy it and paste it. So now I have two identical triangles. These would be similar. Now I can take this triangle and I can make it smaller. And it's still similar to the other one. It shares the same shape. Or I could make it larger. And still similar, it just shares the same shape. So when solving similar triangles, it's important to remember a few things. One is that their corresponding angles will be the exact same size. So by corresponding angles, I kind of mean the angles in the similar position on the other triangle. So if I take this to be kind of the bottom little peak there, that angle we might mark yellow. This angle over here we will also mark yellow, and they would be exactly the same in size. If I took this bottom pink angle here, this angle here would also be the exact same size, and same for these two angles up here. So the size of the angle does not change when you enlarge or shrink your triangle. It's only the size of the lengths that change. And these lengths are going to come in a fixed ratio, which we can use to help solve the problem. So let's take a look at an example. Turn this into an example. So we'll call this length x. We'll call this length 48. Over here we will have 12, 16, and 25. So in similar triangles, we're usually given some information. In this case, the first thing I need to identify is that are these similar? And indeed, I could say that yes, they are, because the matching colors here are telling me that these angles are exactly the same. So the angles within the triangle are the same, therefore it's similar. The next thing I'm going to look at then is trying to solve for this unknown. So the fact that these are very similar allows us to set up a ratio. So the first thing I'm always going to start with is writing the unknown on top of a fraction. X is the thing that I'm looking for. Now what is x similar to on the other triangle? It happens to fall between the yellow and the purple angle. And on the other triangle, between yellow and purple, we see that there's a length of 12. So x is similar to 12, so I'll put 12 on the bottom. So that's my unknown ratio. Now I need to pick one that is known. So the other information I'm given here is the 48, and the 48 goes from green to yellow. So I'm going to put 48 on top. And what's similar to 48? On the other triangle between green and yellow, the similar side, or the corresponding side, is 16. So I've got a ratio, and one thing that I want to keep in mind here is that the unknown goes on top. Makes it easier to solve. The other thing to keep in mind is that on top for both ratios is from the unknown triangle, in this case the bigger one, and on bottom for both is numbers or side lengths from the known triangle. Now we could call the unknown and the known bigger or smaller, but basically what I'm trying to say is that if I call this the big triangle and this guy the little triangle, both x and 48 are from the big triangle, and both 12 and 16 are from the little triangle. So this helps keep our ratios constant, and we need to keep that in mind when you're setting them up. So always on top, both from the unknown triangle, in this case the big one, and on bottom both from the little triangle or the known triangle. And matching up again, the x is similar in position to the 12, and the 48 is similar in position to the 16. So the next step then is just solving this using a little bit of algebra. So that says x divided by 12 is equal to 48 over 16. So the opposite of divide by is times, so we get 48 over 16 times 12. So x in this case is equal to 36. So what we can see, actually, if you pay attention, how do I get between 12 and 36? I go times 3. And how would I get between 16 and 48? If I go 16 times 3, I also get 48. So this bigger triangle is actually 3 times bigger, so all of its lengths should be 3 times bigger. So if we wanted to look for another one, in this case y is similar to which side on the little triangle? It's similar to 25. And we can use another ratio using two sides that are known. So y from the big triangle, so I'm going to use 48 on top, is similar to 16. And in this case, y is equal to 48 over 16 times 25 is equal to 75. Again, 25 times 3 gives us 75, so this bigger triangle is in fact 3 times bigger. Okay, so in this case we see, again, similar triangles always have the exact same angles, and the ratio of the corresponding sides are equal. So one triangle might be 3 times bigger than another, or it might be 0.3 times smaller, but it will be the same ratio for all of the sides. Let's take a look at a second example. So sometimes we get angles that look, or triangles that look like this, and it might be a bit tricky for us to first see why these are similar. So one thing that can be helpful is actually to go ahead and redraw one of the triangles. So I'm going to redraw that A, B, E triangle. It's got a length of 5 and a length of 4 there. Just so I can look at them and kind of try to imagine the big triangle ADC, this big one, and the little one inside of it. So why are these similar triangles? Well, in fact, up here, both triangles are sharing the exact same angle in the original drawing. So this angle over here, when I redraw it, would be the same as in the big triangle. But why would this angle and this angle be the same? Well, you might notice from your parallel line rules that indeed these are corresponding angles. And as we know, corresponding angles on parallel lines are equal. So we do, in fact, end up with this angle here, C, being the exact same as the angle there, B. And likewise, this bottom angle, D, is also the corresponding angle to E. So those angles are exactly the same. And again, one of the hints for us here about it being corresponding is that I've got two parallel lines that are indicated by these little arrows at the bottom. So I know that I can use the corresponding angle rule. So my first check that in fact these three angles are exactly the same for these two triangles is true. So I know these are similar. And the next thing that I need to do is set up my ratios to actually solve the problem. So if we take a look, x is our unknown, and I want to ask myself, x is on the big triangle, and it's similar to what on the little triangle? So again, it goes from yellow down to pink. So from yellow down to pink, the similar side here is 4. And I need to pick a ratio that has two things that are known. So the only other information I've been given are the 5 and the 8. And again, 5 and 8 are going to be similar. And which number do I write on top of the fraction? In this case, I've put x on top, and x is from the big triangle, so I want to keep that on top. So I'll put the 8, which is also from the big triangle, on top, and then I will put 5 on the bottom. And again, using a little algebra, that's x divided by 4 is equal to 8 over 5, so x is now going to be equal to 8 over 5 times 4. We plug this into our calculator, and we actually get a decimal, 6.4. But that's okay. It's fine to get a decimal. These numbers will not always work out perfect for us. So again, we had to prove that these were similar triangles in a sense by recognizing that we've got corresponding angles here with the parallel lines and one shared angle, so therefore all the angles are the same. The sides will have the same ratio. They're similar. one more example here. Again, point to notice, we have parallel lines here, hinted at by these little triangles that they've drawn in there, little arrows that they've drawn in there. So let's take a look and see if we can identify what angles here might be similar. The first thing that I'm going to notice, actually, is that I've got two lines that cross here. So I, in fact, have vertically opposite angles. And we know these are equal. And again, those are the yellow ones. Vertically opposite angles, those are going to be equal to each other. If I wanted to, I could also put in the notation of the little line there. So one little arc through each of those angles means that those are identical angles. And now I need to take a look at some of this other information. So if I actually kind of look at these as parallel lines, draw them in, what I might find is that I actually have alternate angles that show up in here. So in kind of a Z shape, I have angles that are alternate. So I'm going to use pink here. And the alternate angle to that one is in the top of the Z on the other side. So those angles are going to be equal. And I also have alternate angles using these angles here, again following the Z shape. So in fact, I have alternate angles on parallel lines equal, and that's how I get my pink and my green angles to be equal. Okay. Now, just to remind us of that notation, I could also write the pink ones with little double hash marks, meaning that those are the same because they both have two hashes. And the green ones I could make the same by signaling that with 3. So again, the green angles both have 3 hash lines to them, showing that they're equal. The vertically opposite angles here, both yellow, and the single hashes, and then those those alternate angles of the purple that are also equal to each other. Now I have, in fact, similar triangles. Again, I've proven that all the corresponding angles within both triangles are equal. So I need to set up my ratios to find my unknowns. So let's start with x. X is similar to what? Now these triangles are a bit flipped around and twisted if you want to think of it that way, but we've just got to be careful. X is the parallel line along here, so we might suspect it would be the parallel line on the other triangle as well, but let's double check. This X goes between the green and the pink angle, and that 8 also goes between the green and the pink angle, so X is similar to 8. And now I need to find a ratio of two things that I know. Well, again, since x is from the big triangle, I want to pick off a number from the big triangle to go on top. And I'm going to pick 18. And my reason for picking 18 is that I notice that 18 goes between pink and yellow for the angles. And if I look on the little triangle, I actually have a number between pink and yellow on the little triangle as well. So 18 and 6 are the corresponding sides for these similar triangles. And since x is from the big triangle, I'll put the 18 on top, and then I'll put the 16 on bottom. And again, this simplifies by timesing the 8 to the other side. So 18 over 6 times 8, and we get 24. So x is in fact 24. And you could actually pay attention here and notice how, using multiplication, could I get from 8 to 24. I can actually do times 3 again, and you'll notice between 6 and 18 times 3. So these two triangles have a factor of 3 between them. The big one is 3 times bigger. So we might guess, then, that we could find y as well using that ratio, but we'll just write out the ratio here for it as well. So y is similar to what side? Now this flips for us. In this case, y is on the little triangle. So y is on the little triangle, and it's similar, in fact, to 20 on the big triangle, because y is between the yellow and the green, and so is the 20 between the yellow and the green. So y over 20 is equal to, and now we need to figure out what ratio to write for the next bit. So I might choose to use the 16 and 18, or the 6 and 18 again, because they are corresponding sides, they're similar, but which number do I put on the top in this case, the 6 or the 18? Now y is from the little triangle, so I'm going to put the 6 because it's also from the little triangle on top. And 18 I'll put on the bottom because it's from the big triangle. Same with the 20. Using our algebra, 6 over 18 times 20, and we end up getting 6.67. Again, a decimal, but that is just fine. It's not that big of a deal. Sometimes we have to work them out and they end up being decimals. So these are similar triangles. Remember, it can be very helpful for you to highlight the angles that are the same, so it helps you figure out which sides are related to each other. And sometimes you have to pull in your parallel line rules to figure out which angles are actually equal to make the alternate angles. Such as in this case, you'll notice that these two triangles are flipped vertically of each other, but they're also flipped left to right with each other, where the green and the green are on opposite corners.